Looking at section 6.2, example 4, I've got the whole problem already written up here. So this says a company wants to manufacture cylindrical aluminum cans with a given volume, 500 cubic centimeters. What should the radius and height of the can be to minimize the amount of aluminum used? Okay, so I've got a picture of the can here. Height h, radius r, we're trying to figure out what those have to be to minimize the area. Okay, so this is the goal, minimize the area. So first of all, we have to figure out what is the area of this can, and the drawing will hopefully help with that. So what we have to think about is that there's actually 3 different areas that we're looking at here. The area of the bottom of the can, that would be like the amount of aluminum needed to make the bottom of the can. Well, that's a circle, so its area is pi r squared. There's another one of those at the top, another pi r squared, so there's 2 of those. So that's the top and the bottom, that's this 2 pi r squared right there. Then we've also got the cylindrical part of the can, okay? So what's the area of that? For that, you kind of have to picture, well, what happens if I were to cut this can and then fold out that cylindrical part flat? Well, what would its dimensions be? Well, it would have height h, but what would the length then be? Well, the length would simply be the circumference of that circle at the top. So the circumference of a circle is 2 pi r, and then we would multiply that by h, because that would be the dimension that is here. So it's the rectangle with height h, length 2 pi r, okay? So that's the cylindrical part. Okay, then we also have a constraint associated with this thing, so that's this part here. The constraint is that the volume has to be 500 cubic centimeters. So in order to use that, we have to then figure out an equation for the volume of this can. So the volume of a cylinder is it's the area of the bottom of the cylinder, that's pi r squared, multiplied by the height of the cylinder. So pi r squared is the area of the circle at the bottom. Multiply that by h, that gives us the volume of the cylinder. Okay? So now the goal here then is we would like, if we're going to minimize or maximize anything, as we've been seeing, the goal is to write the thing that we're trying to maximize or minimize in terms of a single variable only. Okay? So as we notice here, we've got this written in terms of 2 variables, r and h. So the next thing we need to do is get rid of this h right here. Okay? How are we going to do that? Well, here's our constraint that we got. We know that the volume, as we found right here, pi r squared h must be equal to 500. So what we're going to do with this, solve it for h. Okay? If I solve that for h, I get 500 over pi r squared. What am I going to do with that? I'm going to take it and plug it back up into the h here. That will eliminate the h from this area equation. That's the goal. We would like this to be a function of a single variable. So once we do that, the h will no longer be there, so we can now call this a function of r, a of r. Okay? So what I'm doing at this point is just basically copying that function, but inserting that h, the h that we got here, for the h here. Okay? Once we do that, we notice that a couple things cancel. This is the h that we got. The pi's will cancel, r, and that second power of r will cancel there. So all we're going to have left there is a 500 over r. Multiply that 500 by 2, you get 1,000. So simplifying it, we get this here. And then to take its derivative, let's write that as a r to the minus 1 power. Okay? So the next step, as we've already seen, is to take the derivative. But again, just to sort of visualize what it is we're trying to do here, this function here is telling us the area of this can, the surface area of the can, and thus the amount of aluminum needed in terms of r, okay? Meaning that if I know what r is, then I can find the area of the can by just plugging a particular r value into this function here. Okay, so if I know r, if I increase r or decrease r, this function will tell me whatever the area that corresponds will be. Okay, but if you think about what this graph would look like, it would look something like this. Okay, so I've drawn a little representation of this function graphically. Notice that for smaller values of r, the area is kind of going up. Well, what does that mean? If I've got a small value of r, really small r, what's that going to have to mean? In order to keep the volume at 500, I'd have to have a really tall, skinny can, and so therefore the amount of material would go up. That's why it goes up over here. Likewise, if I have a very large r, and that r will be bounded by, it can't be bigger than a certain quantity, obviously. But if we make it really big, what's going to happen? I'm going to have a really wide, flat cylinder. And again, I'll have to use a lot of aluminum to do that. So the amount of the area will go up there as well. What we're looking for is that sweet spot right there, so to speak, the value that will minimize the amount of aluminum needed. So I'm really looking for that point on the graph of that function. Okay? Well, how do I do that? Well, we realize again that that's a critical number. So if it's critical, that means we can find it by taking the derivative of this function and setting it equal to 0. Okay, so that's what we do next. We take the derivative of that function. Power rule, put the 2 in front, we get 4 pi r here. Same thing here, take that minus 1, put it in front. Lower the power by 1, so here's the derivative. Simplify the derivative by putting that negative exponent, moving the r squared to the denominator. And then, of course, setting the derivative equal to 0 is the next step. So here's the derivative set to 0. To solve that equation, we can move this to the other side. It's minus. We can add it to both sides. And that'll give us this equation here. Okay? From here, we can take that r squared and multiply both sides. That'll give us this equation here. Okay? Again, the goal is to solve for r. So we'll divide by 4 pi. That's the step here. Final step, take the cube root of both sides of this. But we can also realize that 1,000 over 4 is 250. So this is the same as 250 over pi. So r we get there is the cube root of 250 over pi. That turns out to be about 4.3. So this, again, this 4.3 value, that would be the minimum, that would be this r minimum value right here on the graph. That would be the value of r that minimizes a. Okay, so now the question asks us to find h as well. What are the dimensions r and h? So if I know what r is, how do I find h? Well, fortunately, I've got this equation over here again. So what do? I just plug that 4.3 that I got into that equation for h. Okay, so 500 over pi times 4.3 squared. Simplify that, you get about 8.6. So that answers the question. Although the question doesn't ask it, we could find it, and that's what I've done at the bottom here. The minimum actual area. What is the minimum area? So that would be the a value that corresponds to that point right there, the minimum point. Okay, so to find that, I would just take our a function here, that one right there, the 2 pi r squared plus 1,000 over r. I'm plugging in the 4.3 that I got there, and that will give me the corresponding minimum area. So that would be the a min right there, about 349 square centimeters. Okay.